Lab 2, computation of basis and dimension for vector space. Using a Python, we will verify the rank nullity theorem of a given linear transformation and we will compute the dimension of vector. The first program to verify the rank and nullity theorem. Here we have a question, verify the rank and nullity theorem for a linear transformation. That linear transformation T is defined from the space R3 to R3. It has defined as T of x, y, z as x plus 4y plus 7z to x plus 5y plus 8z, then 3x plus 6y plus 9z. Then here we have a program import numpy as np, where numpy is a Python library used for working with arrays. Then from scipy line algebra, we will import the null space. Then we will define the matrix A. So to define a matrix A, we will use the numbering function numpy as np dot array. From the transformation T, we will define the matrix. Since rank and nullity theorem is nothing but the dimension of V must be equal to the rank of T and the nullity of T. For the given transformation, rank and the sum of the given transformation matrix and the nullity of the given transformation matrix must be equal to the dimension of the V. So to find out the rank and nullity, we will convert that transformation into a matrix form. So to write it in a matrix form, as you learned in a theory, we will write the coefficient of x in a one row, then coefficient of y in a second row, then coefficient of z in a third row. So the coefficient of x here is 1. So here we have a 1 in a first row, then coefficient of x is 2. So here we have a 2 in a second place of the first row. Then here the coefficient of x is 3. So we have a 3 in a third place of first row. So here the coefficient of x are 1, 2, and 3 in the given defined transformation. As similar, so as similarly, the coefficient of y is 4, 5, and 6. So it's in a second row. Then 7, 8, 9 are the coefficient of z. So it's present in a third row of a matrix. Once we finish defining the matrix, to find out the rank of a matrix, we have to reduce that into a row reduced echelon form. To operate that, we will use the command rank is equal to np.line algebraic. Then we will use that line algebraic tool for linear algebra operation and to solve a linear equation or to perform the transformation or to solve the matrix equation and much more. So we will use that line algebraic to reduce that defined matrix A into a row reduced echelon form so that we will get a rank of matrix A. Then print the matrix rank by defining that as a rank of matrix. Then we will define the null space as ns. Once we define the null space, we will take that as a print the null space of matrix as ns. Here rank is nothing but the number of non-zero rows and nullity is nothing but number of zero rows in its row reduced echelon form. So once the sum of rank and the nullity is equal to the dimension of V, then we will say that the rank nullity theorem holds. If it is not equal, we will conclude that as rank nullity theorem doesn't hold good. So to define that rank and nullity theorem, we will take that nullity with the shape of A as 1. Then if it holds good, then we will give the command as print the null space of matrix as nullity. If the rank plus nullity is equal to the dimension of a defined matrix A, then we will give the command as rank nullity theorem holds. Else, if it is not equal, means we will give the command to print it as rank nullity theorem doesn't hold good. For a given transformation, rank and nullity theorem holds good. Once we run the program, we will get the rank of matrix as 2, then the null space along with the shape 1. Here we have defined no null space. So that we will get a null space as minus 0.4, 0.8 and minus 0.4. So almost all the values are 0. So null space is 0 elements. Then the null space of a matrix is 1. Here the rank of matrix is 2 in its row reduced form and nullity is 1 in its row reduced echelon form. So 2 plus 1 here, rank plus nullity. 2 plus 1 is 3. Of course, the dimension of vector space here are 3. So defined from the 3. So dimension of a vector space is 3. And if we add the rank and nullity of the transformation, again we will get a 3, since the sum of rank plus nullity is equal to the dimension of the defined vector space. 3 is equal to 3. We will get a conclusion as rank nullity theorem holds.